We're going to present the definite integral. And to get started with that, let's look at the following very, very simple situation. We have the graph of a function. Let's say this is y equals f of x. And we're interested in the part that goes from a point A to a point B. And we would like to be able to compute the area between the graph of a function and the x-axis from A to B. It turns out that this is something that is extremely useful in many, many different situations. And this is why computing areas of this type has been systematized and has given rise to a new notion. So one interesting remark that we should make here is that computing the area and actually defining the area in this case is pretty much the same thing. In general, it's quite a challenge to try to define what we mean by the area of a curvilinear region. There were many different approaches to this, and maybe the most classical one was the method of exhaustion that appeared for the first time in the antiquity, where what people did is, and by saying people here, I should say Archimedes and Evdoxus, not any people, they started building rectangles. They realized that, of course, they can measure rectangles. Certainly by doing so, we get a little less, at least in this picture that I'm drawing here, than the actual area. But then the understanding is that as we refine these rectangles, so we make them have smaller bases, this discrepancy goes to zero. And eventually, through a limiting process, we will be able to get the actual area. And if you like, to also define it. Of course, it took centuries to actually realize this program in an effective way. And what is also, we should set some ideas here. So first of all, there is a symbol for this area. It's called the definite integral of the function f of x from A to B. And it has this symbol that I just drew that might alienate us in the very beginning, because we have, first of all, let's look at what is involved in this symbol. So you have the function, right? The function that gives rise to the graph, and you're interested in finding the area below the graph. Then you have this dx, which at least at first doesn't make too much sense. Why would we put a symbol like that? And that is going to become a little more obvious later when we delve into the notion of the definite integral from a more systematic way. Then we have this symbol right here, which is one way that you can think about it is that this is an elongated S, an S that has been pulled, if you like, both ways. And finally, we have the numbers A and B that are the endpoints of the integral. So this is called the definite integral. Of the function f of x over the interval AB. And let's say what this is. This is the area of the region between the graph of f of x and the x-axis from A to B. Now, computing such integrals is not an easy matter. I mean, think of it this way. Why don't we begin, first of all, with some integrals that we can compute. So let's say how much is the integral from 0 to 1 of x dx. What does that mean? That means that we have the function f of x equals x, whose graph is y equals x, and we're going to go from 0 to 1. And here you can see that this is a right triangle whose area can be computed very, very easily. It has sides 1 and 1, right sides 1 and 1. So this integral is equal to 1/2. Or let's say we wanted to find the integral of a constant function, 3 dx. Let's say this is the interval 0, 1. Here's the graph. We're interested in this area, and this will simply be 3, because that's the area of this rectangle that is being formed. Now, at this point, we should also clarify what happens if the function we're looking at has also negative values, negative outputs. Then we're going to have a graph that, let's say, looks like this, and we want to go from A to B. So this is y equals f of x. And the agreement is that the regions that are below the x-axis are supposed to have negative area, and the ones that are above the x-axis are going to have positive area. So just to give a small example, if we took the function, again, let's resort to f of x equals x, and let's say we want to go from -2 to 1. How much would the integral from -2 to 1 of x dx be? Well, let's start with the negative part. It's below the x-axis, and even though my drawing is not that great because this is not exactly slope 1, however, you have a right triangle that has both sides equal to 2, so its area would be 2. And with a negative sign in front, that would be -2. And then we have the small triangle, which is above the x-axis. As we saw before, this has area 1/2. So the answer here is -3/2. Let's do one more such example. So try to compute the integral of let me write it this way, and then we can, from -1 to 2 of 2x dx. Pause the video, and I'll give you a couple of seconds, and then let's take a look at the computation. So here's -1, here's 1, here's 2. And you have a function that goes, so 1, 2, 3, 4. So it goes like this, right? Here's the graph, and then you have a part which is below the x-axis. So this part here is going to be positive, this part is going to be negative. Again, you have to write triangles. The positive right triangle has sides 2 and 4. So its area is going to be 4. And the little triangle has sides 1 and 2, because when you plug in -1 into 2x, you get -2. And so that will be -1, which is 3. Okay. And finally, let's do a fun example. Compute the integral from -pi to pi of sine x. I mean, at first, you will be thinking to yourself that I'm out of my mind giving you such an integral the very first time that we talk about integrals. However, if we sketch the graph of this function, we will realize that because of the symmetry, this area that you have from -pi to 0 is the same as the area that you have from 0 to pi, only they have different signs. So when you add them together, exactly because this will count as positive and this will count as negative, the answer will end up being 0. One last thing that we should add here is that the definite integral is also usually known as the Riemann integral. As a tribute to the mathematician Bernhard Riemann, who really set the appropriate foundations for the theory of this integral. We have to say that the integral pre-existed. I mean, people were using integrals for almost a couple of centuries before Riemann, but Riemann was the one that actually was able to set the proper foundations for this theory. And that's all. Thank you for watching.